So today, I want to tell you about some of the research that we've been doing at UC San Diego. And the overall sort of overarching theme of my research is I would like to automate programming, right? So just like in other industries, automation has allowed us to produce things with fewer errors and more reliably and more efficiently, right? So similarly, in the software industry, we're hoping that automation will let us produce software with fewer errors and also faster. And of course, this is not a new idea. In fact, automating programming is something that programming languages people have been doing for, ever since they invented programming languages, right? So for example, we used to program in assembly, right? And it was really hard. And then a language like C came along and automated a bunch of stuff. For example, like function calls, right? And then our programs became more concise and more readable, and the whole class of errors just went away, right? And then a new generation of languages came in and automated other things like memory management, for example, right? And our programs became even more natural and concise, right? So the question that I'm asking in my work is, what's next, right? So what does the programming of the future look like? Or is Haskell, in fact, the pinnacle of creation? I'm saying Haskell because I'm a Haskeller, but I know that here at Lambda Days, I've seen most people are into Erlang, so you can maybe replace Haskell with Erlang here. In this slide, it would be just as valid. All right, so how are we going to program in the future? So I would like to argue that probably the closest that we have right now to programming of the future is Stack Overflow, right? On Stack Overflow, I can express my intent, what I want my program to do in a very high-level way, right? So using natural language and maybe some examples, right? And then I wait for a couple of hours or a couple of days, and then the code just comes up, right? And that's great, right? That's exactly basically what I want. But there's a little bit of overhead, right? So there's human effort involved, there's some waiting involved. And so if you think of, the stretch goal for what we're trying to do, right, in our research is to get something like this, but automated, right? So we want an automated programmer's assistant, kind of like this. And so this is where this area of programming languages called program synthesis comes in, right? And in program synthesis, the idea is to enable programmers to express their intent using some kind of high-level intuitive specification, right? And then transform this specification automatically into an executable program by searching in a large space of possible programs, right? And finding one that satisfies the specification. And so what are these specifications that I'm talking about? And in synthesis research, we have tried many different kinds of specifications, right? So some popular ones are input-output examples, assertions, informal specifications, right? Natural language even. And all of these are great, and all of these have their advantages and disadvantages I'm not going to go into detail about. But today, I want to talk to you about a specific kind of specifications that I'm really excited about, and it's types, right? So, and why do I think types are so great? Well, programmers, at least in statically typed languages like Haskell or Java, they're used to types. They're used to communicating their ideas and their intent using types. And just to sort of illustrate this to you, in the Haskell community, so if you've ever programmed in Haskell, you have probably used a tool called Hoogle, right? Hoogle is Haskell's API search engine that is very popular. And in Hoogle, you can search for library functions using type, right? So the same question that I had before, how to split a string at an arbitrary separator, I can phrase it to Hoogle using its type, right? I say I'm looking for a function that takes a character and a string and produces a list of strings. And in fact, Hoogle will answer, right? So it will say, yes, there's a function called split in the library GCUtil that has this type, and it actually happens to be the function that I'm looking for. right? So we can see that types are actually a pretty expressive and concise way to describe your intent, right, as to which program that you want. However, so why is this not yet the future, the program of the future? Well, that's because Hoogle is simply searching in a set of existing functions that someone has already written, right? But how about sometimes, so not every piece of code that I want to write someone has already written, right? Unfortunately. And so we also need some way to generate new programs, right? So we would like to have a way to generate new programs. So this is what program synthesis does. So I'm kind of thinking, some kind of blend of program synthesis and something like Hoogle, right? So that would be ideal. All right, so when I say I want to use types to express my intent, what do I really mean, right? Because programming languages community has invented so many different kinds of types throughout its history, right? And you can kind of, so I'm sort of thinking of types on a scale between sort of simpler types that are more like the types that people use in practical mainstream languages, right? And sort of to the right of this scale are more expressive types, the types that are annotated with extra information. And in this, and of course there's a trade-off, right? Because the simple types are more programmer friendly, but also more ambiguous when it comes to expressing intent, and the expressive types are the opposite. Right? And so today I'm going to show you 2 points in that spectrum, right? So my work falls, in different points of the spectrum. I'm going to show you 2 points. An example of expressive types is a synthesizer that I developed is called Synquid that takes as input refinement types and produces recursive functional programs. And in the second part of the talk, I'll briefly show you a synthesizer that we developed recently in my group called Hoogle Plus, which takes Haskell types and produces compositions of Haskell library functions. Okay, so let's start with Synquid. There's a PLDI 16 paper if you want to read more about this. Okay, so in this part, I'm gonna focus on 2 things. First, how do we even write specifications with types, right? Express specifications with types. And secondly, well, once we have such a specification, how do we do the synthesis, right? How do we search for a program that has this type, right? All right, so in this part of the talk, I'm going to be using a running example of inserting a value into a sorted list, right? So for example, if we have a value like 5 and we have a list like this, right? So we want to insert it into the right place in the list. So how would we implement this function? Well, imagine some kind of simple idealized functional language. We can implement this as a recursive function, right? So I'll call it insert an element X into a list X's, right? So I will have to pattern match on the X's. And by the way, this is not any real language. This is like a toy language, but it's similar to Haskell or Camel, things like that, right? So I'm going to pattern match on the X's, and if X is empty, well, then that's great. We're at the end of the list, which will simply return a singleton list containing X. And then if the list is non-empty, so it has a head H and a tail T, then we will have to compare the new element with the head. And if the new element is less than or equal than the head, then we are in the right place. So we simply prepend X to X's, and otherwise we'll have to call insert recursively on the tail, right? It's kind of simple algorithm, right? But already something to think about, right? So if you implement this by hand, you have to do all these different cases and pattern matching and, remember to compare and whatnot. Right. So our goal is not to have to think about this and not to think about all these corner cases and then how to do this, but rather just to write some kind of high-level specification, give it to a synthesizer, and have this recursive function just come out automatically, right? So we're also willing to provide the synthesizer with the program space, which is in this case would be, we will give it some components that it can use as it's constructing the program, right? So for example, the list constructors such as nil and cons, and we're also willing to say, well, you would probably need a comparison operator, right? Okay, so but how do we describe what we want to the synthesizer. So I told you that types are specifications. Well, that's great. So what would be kind of like a Haskell style type for this function? Well, in Haskell, we would probably write it in something like this, right? So insert takes an A, where A is a type variable, so it's a polymorphic type, takes an element A and the list of A's and produces a list of A's, right? So of course, if you're an actual Haskeller, you would say, no, that's definitely not the type for insert, because you actually need a type class constraint. You need to restrict A to be ordered, but let's forget about this for now, and let's just assume for simplicity that all types are implicitly, they have a comparison operator defined on them. All right, so, but what would happen if we take this simple type, right, and give it to a synthesizer? What is it going to produce? Well, that is actually kind of easy to check, right? So let's ask Synquid what it would say to that. I will go to the demo right now. So hopefully you can see the demo. This is a web interface for Synquid. So here what I did is I just defined my list data type, right, with these two constructors, and I say, well, please synthesize the insert function that that has this type A to list of A to list of A's. So in this in Synquid, you can also name your arguments, right? Because you want the arguments to have names in the program. So if we ask Synquid to synthesize this program, what do you think is going to happen? Let's see. Okay, I see some comments in the feed, so I think you're right. So it could have said nil. Instead, it decided to return its second argument, right? So also not particularly interesting, right? And that's not surprising, because we really didn't tell it anything about this output list, right? Which properties it should have. So so Synquid is very much free to return, so say it's a program that always returns an empty list, or it's a program that always returns a second argument. Okay, so well, right, to fix that, we should probably give the synthesizer a little bit more information about what we want. So in particular, we would like to say that the output list is sorted and that it contains a new element. So the problem was that these sample types are ambiguous, and the way we're going to resolve this problem in Synquid is we're going to give more power to the types, right? So the problem is our types don't have enough power to say what we want to say. All right, so what we really want to say is that, so we have this input X, and we have second input is X, which is a sorted list, and the output is also a sorted list. And by the way, because this allows actually some, doesn't keep track of multiplicities of the elements, but this says sort of enough about what we want from this insertion. Now the question is whether I can write this. So now I describe it to you informally what I want to say. So can I write this as a type? Well, we are in luck, because one of the kind of type systems that programming languages researchers invented over the years is something that can express just that. And this type system is called refinement types. So the kind of refinement types that I have in mind are types decorated with simple logical predicates, right? So for example, if we have a simple type int for integers, we can decorate it with this refinement that says that it's a type of integers whose values are greater or equal than 0. So we are basically describing a type of natural numbers, right? So here, this orange logical predicate is called the refinement, and this new variable is like a special, it's like a keyword, right? That refers to, it's a variable that refers to the value of the type that we're describing. Right, so this would be the type of natural numbers, and you might say, well, how does this help us? Because you're only allowing these very simple predicates attached to types. Actually, magic is going to happen when you combine these refinement types with other features that we have in modern type systems, like polymorphism and data types. Right, interesting things will start happening. For example, you can put this type, this new type nat that you just defined, as a parameter to a list, right? So you can not just say list of int, but you can say list of nat, right? So all of a sudden, you express this universal property that every element inside this list is a natural number, right? And you manage to express it by just using one simple predicate without any quantifier. So usually if you want to say something like that in logic, you would need a universal quantifier, and it becomes hard to reason about. With refinement types, you don't need those. Okay, in fact, I'm going to show you right now how you can use this simple idea of adding simple logical predicates to your types to describe something that we need for this problem, which is sorted lists, right? Okay, let's first start from regular lists, right? So a list data type can be described as follows, right? So we say it's a list with a parameter a, where so it can be either an empty list, nil, right? Or it can be a cons of a head of type A to a tail of type list of A, right? Okay, so this is just simple lists. So now how do we change it to describe sorted lists instead of like any kind of lists, right? Well, the first thing I'm going to do is I'm going to rename it to slist for sorted list, right? So I'm going to rename all of my occurrences of the type everywhere. Am I done? Well, not really, because all I did is just rename it. But so let's see where this definition is currently wrong. So first it says that a sorted list can be an empty list, nil, right? Is that true? Well, that's true, right? Because every empty list is sorted. But then it says that to make a sorted list, we can prepend a head H to a sorted list T, right? Is this true? Well, not really, because the problem is, sure, the tail is sorted, but the head might accidentally be greater than the elements of the tail, right? Then the list is not going to be sorted. So to fix that, we basically have to say that the head is actually less than equal to everything in the tail. How do we say that? Well, it's actually very easy, right? Because as you can see, our the tail, because the slist type is polymorphic, it takes elements of any type, right? The type of the tail doesn't have to be just slist of A's. It can be slist of anything you want. And in particular, what I can say is it's an slist of A's that are greater or equal than the head, right? So this is something you can do with refinement types. And all of a sudden, using just one simple predicate, I have defined a type of sorted lists, which is very cool, in case you didn't notice. All right, so now that we have this type of sorted list, we can actually describe our specification for insert as a refinement type, right? So we can say that now insert takes an slist, returns an slist, and we also want to say that the elements, we also want to refine this return type and say that the elements of return value are the elements of X's union X. And here we can also do that with refinement types. Elements is basically like, you can think of it as a simple recursive function that is defined on the list. Okay, and so if we give this specification now to Synquid, then let's see what is going to happen. I don't want to type it all in, so I'm just going to go to a different tab. But you know, that's exactly what I just showed you, right? So we defined this slist type with that little refinement in here. I also had to define these what they're called measures in refinement types for length and elements, right? So they're just defined for simple recursive functions. And I also had to provide the less than equal as a primitive component that the synthesizer can use. And now I'm all ready to say, well, give me an insert that has this type that you just seen on the slide. And if I run this, then very quickly, you know, Synquid will return the program that we are expecting, right? All right. Okay, so we've seen the magic happen. Now, let me talk a little bit about how it happens, right? So how did we get from this specification to this code? Well, like I told you in the very beginning, program synthesis of today is basically search, right? Search in very large spaces. So if you think of it sort of naively, what is happening here is we take the specification and we take these components that we gave it, and then we start constructing programs, like all programs that can be built out of those components. but right, because there are a lot of programs that you can build out of these components. So, for example, if we are building these programs in the order of size, right, smaller ones to bigger ones, then there are about 2 to the 70th programs that are of the size that's smaller or equal to the program that we're actually, that our solution, right? So this is roughly how many programs we would have to consider, and this is just too many, right? So we won't have time to do that. So synthesis is like search in this astronomically large space, right? And the key idea is that you have to sort of find some way to eliminate large swaths of this space and gradually hone in on like the small part where your program is, right? So the key idea really is you want to be able to reject hopeless programs early. So let me illustrate what I mean by that. So in the picture, in the naive picture that I showed you before, I was basically illustrating how we built the whole program and then we type check it, and then we see if it type checks against this type, and we discard it if it doesn't, right? So with existing, type checking algorithms that so it was published in 2008 by these people, that's the only thing that you can do, because they had this bottom-up way of type checking, right, that required a whole program to be able to type check it against the refinement type, right? So what we want to do instead to be able to reject hopeless programs early is we want some kind of different type checking mechanism that is able to reject partial programs before we have constructed the whole program, right? So we want to construct like a little prefix of a program and then say, no, that's definitely not going to cut it, right? And this is sort of where our work comes in on this top-down way of type checking these programs, right? And the idea is if you can reject just the prefix of a program, then you have automatically rejected a lot of other programs that have the same prefix, right, with just a single check. So let me illustrate how we can do that, right? Rejecting these hopeless programs early. So let's say we have the specification for insertion to a sorted list, and we start with a program that's completely unknown. So first we ask, is this already hopeless? Well, not really, because we haven't filled in anything yet. So we start filling in some parts of this program. So for example, we might decide that the top level construct in this program is a pattern match, but we don't yet know what goes into the branches. At this point, also not yet hopeless. But let's say the next thing that we decide to do is to fill in this first branch with nil, right? So is it hopeless at this point? Yes, this is hopeless. And that's hopeless. Why? Because our specification says that the output list always has to contain the element X, right? And here we're saying, well, in this branch, it doesn't. So it doesn't matter what you put in the second branch. This program is already incorrect. So, and if we're able to reject this program, this incomplete program, then we have automatically rejected about 2 to the 50th other programs, right? So that would be very effective. Okay, and so how can we do this with this top-down way of type checking? Well, so the way our type checking intuitively works is, so let's say, to type check this whole function against this function type, you would have to type check the body against the result type. And so then the type checker can just hone in on, one of the branches and say, well, does this branch have this type? To perform the type checking, it generates some SMT constraints, right? And the SMT solver can tell us whether it's correct or not, right? And the constraint that generates here, well, is it true for all x's that, an empty set is equal to an empty set union x, right? And the SMT solver, of course, says no way, right? For no x, in fact, is that well. So, and it rejects this program, right? So we have rejected this program, and so we have rejected a lot of programs, and that's how it works. And there are, of course, more, there are more intricate kinds of this kind of top-down type checking that Synquid can perform that I'm not going to go in detail here, but you can read about in the paper. Right, so if we have this in place that you have seen, we can generate this insert program very quickly, right? Despite our search space being quite big. So at this point, you might think, well, okay, cool, it can do insertion to sorted list, big deal. I can do that too. In fact, I had it in my first year of college, right? So the question is, can it do something that's a bit less boring, right? So people often ask me, so what's like the most interesting program that Synquid has generated? I want to show you a case study, which I think is kind of neat. And this is a program to convert a propositional formula to negation normal form. Okay, so what's a propositional formula? For those of you who don't know, it's just like a Boolean expression with Boolean variables, right? And things like, logical operators. And what is negation normal form? Well, so this formula that I'm showing here is not in negation normal form. Why? Because so in that normal form, you cannot use implication. You can only use not, and or. Those are the only Boolean connectives that are allowed. And also what is not allowed is to have and. Not is only allowed at variables, right? So you cannot have not and then, some other connector. Right, so, and in fact, there is sort of an algorithm for converting any arbitrary propositional formula into this negation normal form using a bunch of equivalences, right? A bunch of simple transformations. For example, for this formula here, we can first use the definition of implies as, using not and or, right? Then we can use De Morgan laws to distribute the negation over conjunction, right? And then we can use double negation to eliminate double negation, and then we can use De Morgan again, and now we have transformed it into negation normal form. Okay, so now we want to, instead of thinking about this and knowing all of these logical laws like De Morgan and stuff, right? We don't want to know any of this. We want the synthesizer to automatically invent all of this stuff for us, right? Can we do that? Let's see how we can model this problem in Synquid. So first of all, how do we specify it? Well, we can define a type for propositional formulas and a type for negation normal form formulas, and then say we want to go from one to the other, right? So for regular propositional formulas, we'll have a type that has like variables, not, and, or implies, right? All these operations. Whereas for N and F, we will have just a constructor for atom, which can be, a variable or a negated variable, right? So it just says there's a variable name and a Boolean flag for whether it's negated, right? And that's how we model that negation is only allowed at variables. And it also has and or, and that's it. And that's all it has. Okay, so now that we have all those types, we also want to, in our specification, basically what we want to say, I want to go from formula to N and F that always evaluates to the same value, right? So we want them to be equivalent. So to express that, I will define, again, this measure, like this logical function called eval, that basically just evaluates my formula, right? So for variables, I will look up a variable in some kind of environment, where here this environment is basically just an uninterpreted function, right? So we don't know what it is because we don't care. But it is some function. And then it's easy to define, how to recursively evaluate the formula. That's all very easy. And we do a similar thing for the negational form. Formulas also define this eval function. And then finally, we can express our specification very easily by saying we have a formula F, and we want to get the negation normal form formula that evaluates to the same value, right? And this is kind of explicitly quantified over those environments, right, that store the values of variables, even though we don't care what they are. And so if you give Synquid this specification, it takes about 20 seconds. That's why I'm not going to run it for you. But it generates something like this, which is pretty big. And of course, you don't have to read this whole code. But I'm just going to point out some points to you. So for example, this line all the way down there is where it discovers the definition of implies, right? So it says if the original thing was implies, then you're using or of not, right? So here's where the double negation elimination is. Here's where the De Morgan laws are discovered automatically, right? So this is pretty cool. yeah, so we can generate something like this automatically. All right, so at this point, I'm done with expressive types, and I want to talk to you a little bit about what we can do with simpler types, right? So one limitation of Synquid is that, well, you still have to write those specifications. You still have to know what refinement types are, right? So you kind of have to be familiar with logic a little bit. So it can be, you know, hard for just regular programmers, right, to use in their daily tools. So what can we do with simply, you know, if you restrict to simply Haskell types without any refinements, right? And this is exactly what we did in this project called Hoogle Plus that, you know, I again have 2 paper references down there that you can look for more detail, right? And I will quickly tell you about 2 sort of challenges that we faced in this project and how we overcame them. First was how to overcome the ambiguity of these simple types, right? And secondly, as we were proceeding with this project, it turns out that Haskell beginners are not even very comfortable with the Haskell types, right? So how can we help them further, you know, provide those specifications? So just a reminder, the inspiration for this project was Hoogle that I showed in the beginning of the talk, right? Where you can input a type and it will find some library functions that have this type for you. However, the problem is it will only find functions that someone has already written, and it cannot compose functions together to get some new functionality. And this is basically what we wanted to get. So for example, so I'm going to be using a different running example in this part of the talk. So let's say what you want to do is you have a list and you want to compress it. And what I mean by compress is remove adjacent duplicates, not all duplicates, just adjacent ones, right? So if you have a list like 1, 1, 2, 1, what you want to get is 1 to 1, right? And so it turns out that in Haskell, you can do that without writing a recursive function yourself, but just by composing functions from a standard library. So what you can do is first call group that produces a list of lists that groups together adjacent elements that are equal. And then you can map the head function over that list, right, to get the first element from each group. That's how you can do that. But let's say, you know, this is not particularly intuitive, right? So maybe that's not the solution that I would come up with. So I would like the synthesizer to generate something like this for me. Right, so I would like it to work with just the type specification for compress. And you know, what is the type of compress? So you might think, well, the type of compress is just list of A's to list of A's. In Haskell, that's actually, again, not exactly true, because in order to group the elements, we need to be able to compare them by equality, right? So we'll have to provide, again, a typecast constraint and say that those elements of this list should be equatable, because we want to, you know, we want to compare them, and that's sort of what is going on. And so in Hoogle Plus, essentially, you can give the specification to Hoogle Plus, and it will search a bunch of standard Haskell library functions and come up with some compositions of functions that have this type. I was going to show you a demo here, but 10 minutes before the talk, I discovered that the website is down. So I can show you what it looks like, but I cannot run it because reasons. That's very unfortunate. So this is what the website looks like. This is what it should be. And you input your type here, and I can do that, but it's not going to work, unfortunately. Something is wrong with AWS. There's some alarm here. And so what is supposed to happen is that I click the search button, and then it starts giving you some results. Fortunately, I have a slide of what those results would be. So something that you would see is the first solution you would see is this concat group. Then after a while, you will see head of group, last of group, and then finally the fourth solution would be map head of group, which is what I already told you that's what we're looking for. So one thing that's nice about Hoogle Plus is for each solution, it's going to be giving you some example inputs and outputs that this solution produces, and that is supposed to help you figure out what those different programs mean, right? And so by looking at these inputs and outputs, you would see, oh, the first one is definitely not what I want because it did not actually eliminate the duplicates in this list 0, 0, and neither the second, neither the third. But the last one looks like it's something that it could work, right? And so Hoogle Plus would also allow you to your own tests here, right? So for example, apart from the type, I can also say, my input is this, and my output should be Lambda this, right? So I can add that. That's all good, but if I click search now, it's not going to work, unfortunately. And then, of course, if you input that this input, right, then you will only get this last result, the one that you were expecting. Okay, so I promised to tell you, how we deal with the ambiguity of regular types, right? So of course, partially it's just addressed by the fact that we are not generating arbitrary recursive programs. We are just composing functions from the library. However, if you do it naively, you will be surprised at how many irrelevant results you would get. So if we didn't do anything special about it, what would happen is you would get results like this, right? So you would get, a program that always returns an empty list, a program that always returns its argument, a program that takes ahead of an empty list always, right? Obviously not super interesting programs. So why are these not interesting? Well, this one for one always crashes. This one ignores its argument, which is probably not a good thing. Why would I give it an argument if I wanted to ignore it? Those two, like X's and tail, you would think, well, they don't ignore their arguments. However, they ignore the type class that we gave it, right? Why do you say you need to equate the elements of the list if you didn't try to equate them, right? I wouldn't provide you this extra thing in the type if I didn't want you to use it. So all of these, we already know that they're irrelevant, even if the programmer does not provide any additional input, right? Like input output examples. So we would like to be able to filter them out. And so in fact, even if we filter those out, the other problem that we get is we have a lot of duplicate results that produce the same values, right? So for example, these two, for various reasons, they're actually semantically equivalent, right? So, and we don't want to show the equivalent ones. So the way we deal with it is we actually use test-based result filtering, right? So once when we get a bunch of candidate results from the search algorithm, we have a filtering mechanism that is based on property-based testing. It's based on quick check and small check. You can use them interchangeably to filter out the results that don't pass sort of these three crucial properties, right? So we check whether this program crashes on all inputs, whether it has the same, always produces the same output as some other candidate, of course, on some finite set of test cases. So it's like an approximation for functional equivalence. And also whether the output stays the same if you change the input, right? That's an approximation for whether it's using its input. And so the cool thing that we also found out is that those inputs, those examples that we that quick check or small check generate during this test-based filtering, we actually can also reuse those examples to help with comprehension, to help programmers understand what the programs do, right? So like I showed you in one of the previous slides, Hoogle Plus also shows you those small input-output examples next to each solution to show you, how to show what the program behavior. Okay. Okay, and so the last thing that I want to quickly cover is what I mentioned, that beginners might be uncomfortable providing types like this, especially if they have type classes. So this is something that, Haskell types are not particularly intuitive for everyone. So we wanted to provide this functionality where you can only give input-output examples, and we would suggest some types that you might meet, right? And so this, in fact, is what Hoogle Plus does and knows how to do. So the way it does this is, so first when you give it those examples, it infers their concrete types just using, the GC compiler, and then it computes the least common generalization of these types, which is sort of the polymorphic type that captures all of those tests, right? And then it also goes through all kinds of, other more general types that you might have meant, and then it filters out some of the ones that it thinks, are irrelevant for various reasons, and then in the end, it's just left with like a small. So this is what would happen if I entered those two examples. It would offer me 3 different types to pick from, right? And then hopefully I can pick the EQ one because, now it's sort of at least at the front of my mind, what the options are. Okay, and so we evaluated Hoogle Plus in a user study with 30 participants. We gave them 4 different programming tasks, and each task was of the same kind, like this deduplicate task that I showed you. And they had to solve first 2 tasks with just Hoogle and an interpreter, and 2 tasks with Hoogle Plus. And what we found is that with Hoogle Plus, participants were able to solve 51% more tasks, so that's great. So it helped them solve tasks. And another interesting observation was, so we were wondering, is this whole type inference from tests even useful, right? So maybe Haskell programmers are already very good at writing types. Well, it turns out that overall, 42% of queries were made with test only, right? So only 19% were made with type only. The majority, so in fact, about the same, 39% were made with type and test. But if you go to beginners, the percentage of test only queries improves, right? So about half of the beginner queries, the participant could not come up with the type by themselves, right? They only used the tests, which was an interesting observation. So that's all I wanted to say about these 2 systems, and I'll be happy to answer your questions now. Jan, do you want me to stop sharing?
Thanks for presenting. You could maybe stop sharing.
Mm-hmm.
So I saw plenty of questions in the Q&A tab. So if you ask a question, please raise your hand so we could invite you to the stage to ask the question in person. Okay. So Piotr, I think we can hear you now.
Hi, I would like to ask a question because there is such thing as a free theorem. As you probably know, this is a theorem that could be proved by just using the functions type, nothing more. So my question is, do you think that it somehow could help to reduce the space of possible results while searching the function?
Oh yeah. It's that's a great question. Thanks, Peter. So in fact, free theorems help us a lot as we're doing the synthesis from types, right? So basically, if you try to provide non-polymorphic types as your specification, you're doomed. You will get so many irrelevant results, right? Whereas polymorphic types, just by themselves, just by their nature, right, of how they, so this is how basically free theorems show up in this setting, right? Is that polymorphic types already by their nature, they really restrict the set of programs that type check, and that really helps us, right? So if you think of something like if I want to synthesize a function in Haskell, it's called replicate, right? It takes an a and an int and then produces a list of a's, right, of that of the size that you gave it, right? So it's enough to say that the size of the list is equal to that second argument that you gave it, right? Then and the fact that every element in the list will be equal to x, right, the first argument that you gave it, that's going to fall out automatically just from the type being polymorphic. So yeah, in fact, it gives us, it makes the specs much more concise and gives us stronger guarantees.
Thank you very much.
Thank you, Piotr, for asking the question. And John.
Oh, John.
Hello, Nadia.
Hi, John. How
Talk.
are you?
So I wanted to ask you, while you were talking about Synquid, whether there was a nice way to include some examples to guide the synthesizer as well. And then you did exactly that with Hoogle Plus. But I thought it's still worth asking the question, if you go back to Synquid now and the refinement types framework, is there a nice way there to make good use of examples?
Yes, this is a really good question indeed. So, I mean, of course, one thing you can always do is the post filtering, right, which is something that what we do in Hoogle Plus. But I think the interesting question is, can you do something more, right? So can you integrate examples during search and use them to speed up the search? And in fact, we now have sort of two different lines of work going on that along those lines. So one line of work that my student Tristan is working on is he's developing this type-driven synthesis framework where the idea is, well, you just give it a type system, or rather you give it a type checker that's implemented in like a little bit of a special way, right? And then it gives you a synthesizer for free for that type checker. And one of the things that we want to play with this framework is, well, what if you give it two different type checkers, right? Two different type systems, and then you can give it multiple specifications expressed in those different type systems, and both of those type checkers will be kind of like filtering out those partial programs as the synthesis proceeds, and both of them will be contributing to the search. And then you can make one of those type checkers be something like what's implemented in the myth synthesizer, right, which takes input-output examples and filters based on that, right? And then the other one could be something like Synquid, and the third one could be something like our other work on resource-driven synthesis, right, where you provide resource specifications for your programs. So I think that's a neat way to combine these two. But we have another project going on where we are sort of like trying to blend refinement types and examples and do something in between, which is essentially we are adding intersection types to refinement types. And so if you have intersection types, you can basically say, well, my function has both this type and this type. So you can say something like, on this kind of inputs, this is how it behaves. And on this other kind of inputs, it behaves a different way, right? So you can use this intersection types both to provide concrete input-output examples, but also to provide something like more general, right? So for example, you can say, a good example of something that would benefit from this is, let's say you have a function that takes a list of integers and returns a Boolean that says whether all the elements are negative, let's say, right? It's a little bit artificial example, but something like this is basically impossible to specify in Synquid. And it's also very hard to specify with just examples because the output is Boolean, so you usually need a lot of examples. However, with these partial refinements, for example, you can say something like, well, if I have a list of non-negatives, then it returns true, right? And then in addition to that, add a couple of concrete examples. Yeah, so those are the two things that are going on.
So I guess if you were trying to synthesize a sort program, it's easy to give an incomplete specification of sort. But if you also said it's the identity for any ordered list, then that might prevent it from discarding duplicates, for example.
Right. So that's a very good point. Yeah. So sometimes there are some kinds of inputs on which it's easy to provide a specification that is not quite a concrete example, but it's yet a partial specification. Yeah.
Yeah. Super cool. Thank you.
Thanks for your question.
John, thanks for your questions. So once again, let's give a warm round of applause to Nadia for the great presentation. Unfortunately, the time is up.
Thanks, everyone.
Basically, if you'd like to talk more, ask more questions, I would like to invite you, Nadia, and all of you to the lounge section. And over there, you can take a seat and chat at the speakers table. So the last agenda for the day is a replay of today's keynote. That was the Excel meets Lambda. The presentation was delivered earlier today. So if you haven't seen it, I totally recommend it. It was really excellent talk, and I really enjoyed it. So yeah, once again, thanks for joining, and see you at our next sessions.